Even though this video is about the Sylow theorems, and I'm going to start with the chapter in Galilean, which is the one that I just finished covering and doing all the problems for, attempting them at least. And I think I got a few right, which is wonderful. I'm going to go through multiple books. In this particular case, I think I'm going to take my time. But also, you'll see how different it is to treat subjects in different abstract algebra books, how some subjects have to be introduced before others, but in some cases, there's actually a lot of leeway for how some other subjects are brought in. In the case of the Sylow theorems, what is always brought in is Cauchy's theorem, but sometimes it's brought in first, and then the book will go into the Sylow theorems, and then also the class equations. Some books will bring it at different times, and may not even bring it in at all. But that's how Galilean chose to do it. He chose to talk about conjugacy classes, then the class equation, which is a way to take the order of the group and do a sum where you pick of every element, you pick the conjugacy class that it's in and get the order for. And so it's not, you're only picking, if two elements are in the same conjugacy class, that only counts once. That's basically what the statement says here, over one element A from each conjugacy class. You'd have to see it with examples. Yeah. And then the first Sylow theorem says, for G finite group, let P be a prime. If P to the K divides the order of G, then G has at least one subgroup of order P to the K. So they exist. And that's where you find them. You find them in a group where P to the K divides the order of that group. And then the P subgroup itself, of course, it's always the highest of the power of that prime. All right, so that's why P to the K plus 1 does not divide the order of G. So for example, and it's mentioned here, if there is a 2 to the third in the power of the group, the order of the Sylow 2 subgroup is 8, not 2. And the same if it's 5 square, 5 to the fourth in this particular example, it's 625. That's a key distinction. Then the whole business about conjugacy. Then Sylow's second theorem, which is about conjugacy and subgroups. So if H is a subgroup of G, and the order of H is a power of a prime, P, then H is going to be found somewhere in some P subgroup of G. Then the real workhorse is Sylow's third theorem, where you do 1 mod P for this prime, and if it's 1, then that group has Sylow P subgroups in certain numbers. So it's a very complicated calculation. If you look at my updates for Galilean, you will find those sorts of examples of how that is calculated. And then, of course, if in a particular group, it's only got one Sylow P subgroup for that prime, then it's normal. It's a normal subgroup. And the normalizer of that normal subgroup is the group itself, G. Some conjugacy work, and then some calculations with the theorems for specific orders of groups, and then some calculations to determine how many groups there are of that order. So the Sylow theorems are used for, you get a lot out of just being given that order on some very small condition, very small number of conditions. And it ropes into finite simple groups because it is one of the tests to cancel, to say that some group is not a simple group. And then that ties into the simplicity of A5. And so you're going to see through all these books that I show those themes. Simplicity of A5, the use of the Sylow's third theorem to determine whether a group is simple or not, and then all kinds of calculations about how many groups are there of a given order, and then how many different subgroups does a specific group have just by being told what the order is. Okay, so now a little bit of a historical note is in the case of an older book like Herstein's Topics in Algebra, you'll see how, by the way, Birkhoff and MacLean doesn't even have this content. I have the book somewhere. and it doesn't have it. So in the case of Herstein, this is all there is for Sylow's theorems. Not only that, but Herstein only talks about the first one, proves it via combinatoric means, very interesting. And then the second and the third are somewhere in here and left to the problem. So you really, in the case of Herstein, you actually have to solve problems 21, 22, 23, and 24. And those would be the proofs of the theorems. Okay, so then the next book, and I'm going to run through a whole bunch of them. So if you are into this, you're going to love it. If not, it's going to be a lot of Sylow theorems in different books. In the case of Alufi, Alufi's Notes from the Underground, he does a great job to combine everything in a very succinct way. Okay, so he's got dimension of conjugacy, the class equation, talks a little bit about classification, and then lays out all the Sylow theorems, gives an example for how in simple groups you classify out groups that are not simple, okay, and then does some calculations, but from the perspective of simple groups, which is really done in chapter 25 in Gallian, and then actually works out the proofs to the theorems in a separate subsection, and then goes into the simplicity of A sub n, not just focusing on A sub 5, because A sub 5 is the smallest one that is simple, but it's really A sub n for n greater than or equal to 5 that is simple. And then he also lays out, okay, how to do the proof of the simplicity of A5, which Gallian did not do. Okay. And then Alufi also, interestingly, ends up with the concept of a solvable group, okay, which says if group G is solvable, it emits a normal series. All these groups that have had all their normal groups taken out, such as the quotients, are abelian. And this actually is found in Gallian in the section on Galois theory. It's actually not in the Sylow theorems. Okay, so then I'm going to move on to our friendly dictionary of abstract algebra and just show how Dominant Foot does it. So they have a section named Sylow's theorem, and in their case, and I've mentioned this in some other video, instead of breaking them out as 3, they just call it Sylow's theorem, and really each one corresponds to the first, second, and third in Gallian. So the one that does 1 mod p is number 3, the one with conjugacy and subgroups is number 2, and the one that says the p groups exist is number 1. And then he goes into, they go, because it's Dominant Foot, there's 2 dudes. They do the proof right in here. Then they jump into examples, type PQ, order 30, of figuring out, based on the order, how many P subgroups does that group order have. Groups of order 12, they do here. They do P square Q, and then A5, which is order 60. They don't call it that, but really, it's A5. So A5 is simple. And then the proof, I think that's all they really do for it. Yeah. But then they go into the full proof of the simplicity of AN. AN is greater than or equal to 5 in detail. Then when we jump to the whole classification business that they do, that's where they use the Sylow theorems for classifying groups. Groups of order P cubed, order 30. So Sylow theorems are all in here under various, put to various use. Then they also have some applications for group theory, and this is where they get into the whole simple groups business. And of course, they use normalizers of intersections of Sylow P group subgroups. So they put the Sylow theorems to good use for simple groups. And that is Dominant Foot. Now the next one, and this will be a book very similar to Gallian, which is Hungerford. Hungerford talks about solvable right here. and then goes into the simplicity of A sub n with a proof, detailed proof, and then has the Sylow theorems later. Of course, Cauchy's theorem is always mentioned with the Sylow theorems, first, second, and third, named very much the same way as Galilean does, with the examples put in order 56. Talks about conjugacy, and then goes into the actual proofs of the theorems with some problems. Yeah. Then, now in the case of Rotman's undergraduate book, even though it's a smaller book, Rotman does a really good job of putting it all in a section, in a single section. Groups of small order, Cauchy's theorem. Then there it is, Sylow P subgroup, the definition. Isomorphism criterion. Every element in A5 is a product of 3 cycles. So in a very brief set of pages, Rotman lays it all out. But because there isn't the space, he's not doing as many calculations as the other books are. Yeah, there it is. Sylow theorem. And there's the 1 plus Kp. So that's the third theorem. Yeah. So brief, to the point, but it's in there. Then in the case of Fraley, talks about simple groups early. Group is simple if it is non-trivial and has no proper non-trivial normal subgroup. And then they have the Sylow theorems in their own section, talking about the normalizer. First theorem with a proof, second one also with a proof, and the third one also with a proof. And then jump into some applications. The HK business that I need to get much better at, right here, where you have multiple subgroups that are of the same order. This is used a lot in some of the problems. Where you want to say how many elements of a given order are there. Or if there are multiple subgroups and they have the same element, you've got some overlap. So you actually have fewer elements in a number of subgroups. Yeah, so that is Fraley. Then in the case of Silverman, Silverman talks about the Sylow theorems, I would use the word briefly, but where Silverman really, he uses also the combinatoric way in which Herstein does it to prove, yeah, he uses it somewhere in here. The first theorem, yeah, it's used in the proof. But then I think where I like the way Silverman covers material is when he goes into simple groups, because he's got a really nice proof of A sub n greater than or equal to 5. At least I mean, it's the same proof that other people are doing it, but he lays it out really well. Yeah, with all the various cases. Okay, so that's Silverman. Then, in the case of Rice and Rankin, Rice and Rankin talks about the simplicity of A sub n first. Talks about the normalizer. Yeah. And does a proof. And then later on comes back to group theory and does the Sylow theorems. First one, the second one, and the third, with somewhat brief proofs, and then does a bunch of applications. Yeah. Some examples. Yeah. That's Price and Rankin. And then I'll finish up with Artan. And in the case of Artan, he does lay out the geometry of it better, in my opinion, because he's looking at the pictorial representations of groups as well. There's a little bit of geometry and a lot of linear algebra in this book. And so that's A5, the dodecahedron. Yeah, and then he does the proofs. Here's that combinatoric term that is sometimes used in the proofs. And then he's got a really nice section for the groups of order 12. And here are the proofs. Yeah. Okay, so that's it.